Okay, okay. So what is the name of the title, by the way? This is from the textbook. Okay, your syllabus says the Z transform. The title here is representation of signals using discrete time complex exponential. That's what your Z transform is all about. Okay, so to relate this better, let me just go through the other transform that you have been studying all this is, right? The Laplace transform. You have studied Laplace transforms, right? What is a Laplace transform? What all things you are doing with the Laplace transform, by the way? You have studied Laplace transform in your network theory, remember, where the integral differential equations, right, representing first order, second order circuits and all, that will be converted into normal equations containing multiplications and divisions, right? So analysis becomes little simple. Okay, and in your control systems also, what all things you are doing, by the way? I think in your control systems you have this the topic stability analysis, root locus, Bode plot. In all those chapters that are going to come next, you will find out that you will be always manipulating in the S domain only. You will be manipulating S domain, that is the Laplace. Okay, so in Z, okay, so unfortunately this Laplace transform exists only for continuous time system. So this Z transform is something similar to Laplace, but exclusively for discrete time systems. Okay, so what all things we can do with Z transform? We can study the system characteristics, right? Looking at the Z transform of any given system, we can predict whether the system is a stable or it is causal. Okay, those things can be predicted using Z transform. Then what all things you can do? We can get the computational structures. Okay, we can get the derive the computational structure. What is the computational structure? Somebody gives you a problem and gives you a formula. Say, so you are given a difference equation, then you have to get a circuit from the differential equation, right? Just like from the differential equation we can get a circuit, from difference equation also we should be able to arrive at a circuit, right? Z transforms allows you to do that. And you can also solve the difference equations. What are difference equations, by the way? Just like your continuous time systems, right? The LCR circuit, so and so, they have differential equations. Discrete time circuits, they have something called as difference equation. Let us say as and when the time comes. So for the timing, let us understand that Z transform is a discrete time counterpart of Laplace. Okay, then let us just compare, the formula, right? What we had in discrete time, what Laplace transform, by the way? In Laplace, you had this formula, right? So this is what your Laplace is. So what do you do here? X of t e to the power minus ht and an integration. Integration because Laplace was continuous, right? For existed for x of t, the continuous. Here we have discrete time. So since our signal is discrete time, instead of integration, we will have the summation. Instead of e to the power minus ht, the complex, continuous complex exponential, right? Where you have been taught that s equal to sigma plus j omega. So e to the power st, see this particular term, right? So it was all about x of s means what will be done? You will be representing the given signal x of t in terms of continuous time complex exponentials. Here what we are doing is we will be representing x of z, we will be representing x of n in terms of discrete complex exponentials. Okay, we'll be representing them in terms of discrete complex exponential. Here z is given by r e to the power j theta. Okay, got this thing? So something similar to, and the plane, by the way, we all know, right? Your Laplace, it is given by this S plane, right? S plane, we remember this. There will be something called as poles and zeros. Even in Z transform, we will be getting some poles and zeros, right? Your S plane, what it is going to contain? S equal to sigma plus j omega, right? So it's going to contain some sigma and some real axis and imaginary axis. Whereas Z here is actually given by some r e to the power j theta. So it's going to contain certain radius. Okay, it's going to contain certain radius, and then it's going to contain, so every point will be, say there is a point here, it will be represented by certain radius and certain angle. Okay, r e to the power j omega, sorry. Okay, so that is how this is going to be. So with this brief introduction, let me tell you that the Laplace, whichever you studied all these days, did not exist for discrete time systems. Okay, that is why we needed a tool which can do all the things that a Laplace transform can do, but for discrete time system. That is why Z transform. Okay, that is one thing. And second thing, let us remember that even the Laplace or the Fourier or the Z, even you have done this in, they do not exist for periodic signals. The transform exists only for aperiodic signals. Okay, there is one more thing. Okay, later you should not, you know, wonder why I am not finding this thing for a sine wave or a cos wave. Very seldom we do that. Okay, because they exist only for aperiodic signals. Okay, now let us straight away go to the formula of the Laplace. Let us not Laplace, sorry, Z transform. Okay, let us go to the formula for the Z transform and get started. Okay, so here we have okay, what is a Z transform, by the way? So it comes with a very simple formula. Okay, so you will be given an x of n, which is aperiodic in nature. That is why you will integrate from minus infinity to plus infinity. That is why you will be integrating from minus infinity to plus infinity. X of n, z to the power minus n. Okay, that will be the formula. And inverse Laplace transform comes with the 1 by 2 pi j. Okay, so Laplace in Z transform is existing for a periodic signal, but Z transform is periodic. That is why while finding an inverse, we will be dividing it by 2 pi j. We will be dividing it by 2 pi j. In this particular thing here, this is called as circular integration. It will be an integration over a perimeter of a circle. It's a circular integration, but thank God we will not be solving the problem of finding the inverse with this formula. Rather, we will be using ready templates. Okay. Okay. So here is the formula. So without wasting much time, let's quickly get started with the Z transform. Okay, let's quickly get started with the Z transform. Okay, once again, what's the formula? X of n, z to the power minus n. Okay, so here is the problem. So here, let me start with three basic signals. Okay, let me start with three. See, you can see this first signal, second, and the third one. Now, tricky thing is you can see the arrow. This first signal here is a right-sided signal. Okay, it's a first signal is a right-sided signal. Second signal, you can see here is my arrow. So this one is a left-sided signal, and this third signal is both sided. It's a two-sided. Okay, it's a two-sided signal. Some values on the left side also and some values on the right side also. Keep this thing in mind. Now let us start. Now let us start. Okay, the first question here. The first question here. Okay, find the Z transform of the first signal. What was the signal, by the way? The signal is here 1 2 minus 1 1. Okay, the signal is 1 2 minus 1 1. Okay, should I write it once again here? 1 2 minus 1 and 1. Okay, and the arrow is here on the at here. Okay, the arrow is here. Okay. So now what is the formula? So now do we need to do from do the summation from minus infinity to infinity? No. Since the signal starts at 0 and goes till 3, I will integrate from 0 to 3 only. Okay, I will integrate from 0 to 3 only. So let us expand the formula. X of 0 into z to the power minus 0 plus x of 1 into z to the power minus 1, x of 2 z to the power minus 2 plus x of 3 z to the power minus 3. Okay, so if at all I substitute here, x of 0 is anyway 1, x of 1 is, see, the x of 0 is 1, x of 1 is 2, x of 2 is minus 1, x of 3 is plus 1. Okay, let us substitute z to the power minus 0 anyway. Okay, the first term anyway is 1. Then z to the power minus 1 is z to the power minus 1 2 into, and so this is my Z transform. Okay. Now, unlike your Laplace transform or the Fourier transform, Z transform comes with one more term. Every Z transform x of z has to be accompanied by this particular term. It is called as ROC. ROC means the region of convergence. Okay, so whenever you say a Z transform answer, it has to be accompanied by certain ROC, the region of convergence. What is meant by convergence, by the way? I think you remember, right? Convergence is a word which is related to the stability. Okay, so it means those values of Z. It means those values of Z for which this x of z. It is those values of z for which the x of z will be giving us finite values. Okay, they will be the in the area region of convergence. Okay, that means, for example, now can you tell me for all values, you can see here in this particular expression, so this is 1 plus 2 divided by z minus 1 divided by z to the power 2 plus 1 divided by z to the power 3. Okay, that's how it is. So if at all I put z equal to infinity, what's going to happen? So shall I write this thing? So this here is 1 plus 2 by z. Okay, 1 plus 2 divided by z. Okay, 1 plus 2 divided by z minus 1 divided by z square plus 1 divided by z to the power 3. 1 divided by z to the power 3. So now, if at all I substitute even z equal to infinity, 1 divided by infinity, 1 divided by infinity, 1 divided by infinity, it's going to be 0. So for all the values of z, this thing is 0, except what will happen if I substitute x equal z equal to 0? If I substitute z equal to 0, then what's going to happen? 1 by 0 goes to infinity. So I would say that this particular term here is converging, right? It's going to give me finite values for all the values of z except for z equal to 0. So my region of convergence ROC is entire z plane. Okay, entire z plane except z equal to 0. Entire z plane means what? All the values of z except z equal to 0, or which exists at the origin. Okay, okay. So what was the signal, by the way? It was a right sided signal, and there you got the answer: 1 plus 2 z to the power minus 1 minus z to the power minus 2 plus z to the power minus 3. ROC was entire z plane except z equal to 0, the origin. Okay, okay, shall we? We'll continue now. Let us go to the second question. Now let us go to the second question. What happened there? Now see the second question here. It's a left-sided signal. Second question here. It's a left-sided signal. So what do we have? The signal starts from where? This is 0, minus 1, minus 2, minus 3. Okay. So z to the power 3. Why is it so? Z to the power minus of minus 3. Okay, so z to the power 3 plus 2z to the power 2 minus z to the power 1 plus 1. Here is my signal. Of course, as I said, you give the z transform along with ROC. So here you tell me whatever may be the, if I substitute z equal to 0, what's going to happen? 0 plus 0 plus 0 plus 1. Z equal to 100. 100 to the power 3 plus 2 into 100 square minus 100 plus 1. It's also going to be finite. So all the values of z except z equal to infinity are going to give me a finite value for x of z. So here I say that my ROC is entire z plane except z equal to infinity, except z equal to infinity. Okay, so I have shaded the entire region here. In the previous one also, in the previous numerical also, it was entire z plane. So I should plot like this: z plane to take one horizontal, one vertical axis, mark the real and imaginary, and simply shade the entire area. That means entire area, what does it mean? All values of z. Okay, all values of z. Now this is a third question. You can see values on the right and values on the left. So signal starts from minus 1, goes till plus 2. Okay, so what does it mean? So it's z transform z plus 2 minus z to the power minus 1 plus z to the power 2 here. Okay, now if at all I substitute z equal to infinity, if at all I substitute z equal to infinity, here it will be 1 divided by infinity. This will go to 0. Okay, if at all I substitute z equal to infinity, this will term will go to 0, this term will go to 0, but this term will go to infinity. So x of z gives me infinite value if z equal to infinity. If at all I substitute z equal to 0, then this is 0, this is 2. Here 1 by 0 is infinity, 1 by 0 is infinity. So in this particular case, okay, one second. Okay, so okay, let me come to that. Okay, let me come to that. Okay. So here, what is happening? Just see the expression here. What is x of z? X of z is z plus 2, z plus 2 minus 1 divided by z minus plus 1 divided by z square. Okay. With this particular expression, now let us understand what is meant by ROC. If at all I substitute z equal to 0, then what's going to happen? If at all I substitute z equal to 0, what's going to happen? 1 divided by 0, right? 1 divided by 0. This entire term, 1 divided by goes to infinity. So this x of z will give me infinite value for z equal to 0. If at all I substitute z equal to infinity, then here, see, you can see this term will go to infinity, whereas other terms go to 0. But since this term goes to infinity, x of z once again goes to infinity. So ROC, the region of convergence, that means what range of z values are there for which x of z gives me finite values. So what can we guess? Except for z equal to 0 or z equal to infinity, for all the values of z, x of z is going to give me finite value only. So my region of convergence includes entire z plane once again, except origin, right, and infinity, plus or minus infinity. Okay. That is the meaning of the region of convergence. Okay, so we have seen three types of problem now. One signal was right sided, another signal was left sided, another signal was both the sided. Okay. ROC here in all three cases was entire z plane, the region of convergence. That means x of z would give me whatever value substitute, 2 lakh, 3 lakh, 4 lakh, or minus 95. It was giving me finite value only, except z equal to 0 or z equal to infinity. Okay. Okay. Now let us see the next question here. Now let us see the next question here. Okay. Next question here. Okay. What is the signal here, by the way? Alpha to the power n into u of n. Okay. Now compared to the previous questions what we saw, all those questions, the signals were of finite duration, whereas you can see this particular signal here is of infinite. We remember alpha to the power n into u of n, right? This signal here is of infinite duration on the right side. If alpha is greater than 1, it's a growing exponential. Okay. If alpha is less than 1, then it is a decaying exponential. Okay. We remember this, right? We remember this. So now let us get started with this. Okay. Now let us get started with this. So what is the formula? X of n, z to the power minus n. Now remember. So what we are doing here is, look at this expression here. We are putting alpha along with this guy z here, right? You are putting alpha along with this particular guy z here. So what's going to happen is, okay, let us substitute 0 to infinity, right? The conventional formula is for minus infinity to infinity. Now since u of n, alpha to the power n to u of n, this exists only on the right side. So this is 0 to infinity. Let us take them in the bracket. Okay. So let us assume that this term will be less than 1. Okay. Let us assume that this term is less than 1. Then the formula will be 1 divided by 1 minus alpha into z to the power minus 1. 1 divided by 1 minus alpha, right? That's the formula for anything that goes from 0 to infinity. Or what this alpha divided by z just goes here, then in the numerator. So z equal to x of z equal to z divided by z minus alpha is my z transform. Okay. This is my z transform. Now the next question is, what is my region of convergence? What is my region of convergence is the next question. So how do we determine region of convergence? It is those values of z. What is region of convergence? See, look at the question. For what value of z, x of z is stable? For what value of z, x of z is unstable? Okay. Now, by the way, do we remember this thing? By the way, this number here is alpha, right? Now we know one thing. For alpha greater than 1, it's a decaying, growing exponential, right? We remember it, right? Just in the backdrop. Okay. I don't know whether it's how relevant it is. For alpha greater than 1, you can see for alpha greater than 1, this is a growing exponential. For alpha less than 1, this is always going to be a decaying exponential, right? Let us remember that. Okay, okay, let us go back to the analysis. Okay. There are here is the expression. So how do we determine ROC? ROC is not determined from the answer, but this is the point here, right? Here in the summation. Now look at this particular thing, x of z, x of z. Okay, the requirement is here also the expression is still valid, right? Requirement is if this particular term in the bracket is less than 1, then only this particular infinite summation, see here, if this is less than 1, the infinite summation converges. If this number is greater than 1, then the infinite summation diverges. That means for us to be getting a stable system, alpha into z to the power minus 1, this particular term should be less than 1. Okay, you see here the magnitude sign. See the magnitude sign. We are not bothered. Okay, if this gets some e to the power j theta, magnitude of e to the power j omega s will be 1 only, right? So whatever may be the phase angle, whatever may be the sign, plus or minus, we want the magnitude to be less than 1, so that this particular term here gives me a finite value. So alpha z to the power minus 1 is less than 1, or it says that z comes here in this particular side, magnitude z greater than alpha. For all magnitude z greater than alpha, x of z is finite. Okay, okay, got this particular thing. So hence we get the z transform. So this here is the z transform. Okay, just like your Laplace, z transform is represented by a circle of certain radius. Okay, so z transform is represented by a circle of the radius. Okay, represented by circle with this particular radius. Okay, that is one thing. And yeah, what other things are there, by the way? Yeah, there is something called as poles and zeros. Do you remember poles and zeros? Now look at this expression here. Let me clear this. Look at this expression here. Those values of z, which make x of z go to 0 are called zeros. Those values of z which will make x of z goes to infinity are called the poles. Okay, if at all I substitute z equal to 0 here, what's going to happen? Okay, so this entire x of z is going to go to 0. So equate the numerator to 0, you will get 0. Here there is only one z, so that means now we have 1 0 at the origin. Similarly, equate this denominator to 0. Equate this denominator to 0. This will give me z equal to alpha, right? This will give me z equal to alpha. That means if at all I substitute z equal to alpha, x of z, z divided minus alpha minus z minus z, what's going to be 1 divided by z divided by 0, right? It will straight away shoot to infinity. So there is one pole at z equal to alpha, and there is 1 0 at origin. Okay, so this is how a typical z transform problem looks like. So it will contain the plot of region of convergence. What is region of convergence? Those values of z for which x of z is going to give me finite values. So here author says that any value of z, if the relation is maintained that z is greater than alpha, if z is greater than alpha, you can see here, what is this particular term? This is alpha divided by z, right? Got this particular thing. So this particular term here is alpha divided by z. If z is greater than alpha, then what's going to happen? The denominator, since it is greater than numerator, this particular term is always less than 1 only, right? That's why it will always turn out to be a decaying exponential only, which will finally converge. Okay, which will anyway converge. Okay, so that is the idea of this particular z transform. Okay, got this particular thing. And one more interesting thing that I want you to observe is, in all the previous cases, right, in previous 3 problems that we saw, ROC was entire z plane, right? ROC was entire z plane here, entire z plane here, and in the previous problem, ROC I said was entire z plane. Any value you substitute for z, as and when it is not equal to 0 or infinity, x of z was always finite. Whereas for this particular problem, ROC is any value of z greater than alpha. If ROC is less than alpha, alpha divided by 2, if I substitute, it is going to give me an infinite value. Okay, that is why ROC is not entire z plane. Okay, so one thing we will conclude that those signals which are having finite duration will have ROC as entire z plane, whereas this particular signal was of infinite duration. That is why here ROC is not entire z plane but only certain region. Okay. Second thing that we saw was poles and zeros. So what was poles and zeros once again? So those values of z which will make x of z goes to 0, they are called as zeros. Those values of z which will make x of z goes to infinity. See here, if it all substitute z equal to alpha, z divided by alpha minus alpha, 0, 1 divided by 0, z divided by 0 goes to infinity. So those values of z which make x of z goes to infinity, they are called as poles. A 0 is marked by a circle, pole is marked by a cross. Okay, got this thing? Okay, so that was that. Now let us see one more problem. Okay, now see, this particular question was alpha to the power n into u of n. Now the second question is alpha to the minus alpha to the power n u of minus n minus 1. See, the tricky part here is this particular question. See the z transform here. The z transform for this question is also z divided by z minus alpha. Okay, so the previous problem what we saw, alpha to the power n into u of n, right? There also, in the previous problem also, our z transform was z divided by z minus alpha only. There also it was z divided by z minus alpha. Okay, and for this particular problem also, z transform is z divided by z minus alpha only. But the first problem what we saw, my ROC was outside a circle. Okay, right? The ROC was outside. Here you can see ROC is inside the circle. Okay. So that is why I said every Z transform answer should be accompanied by ROC, because two or more signals can have the same Z transform, but their ROC will be different. That is why it's important to mention. Okay, now let us see how this question is different. Okay, what is the signal, by the way? Once again, it is alpha to the power minus alpha to the power n u of minus n minus 1. So minus of alpha, that means since there is a minus sign, amplitudes are going to be negative. Okay, alpha to the power u of minus n minus 1. See, for this thing what you have to do is, first you have to do the shifting, u of n minus 1, then n shall be replaced by minus n. So this here is my question. So from where to where? Now this signal you can see starts from minus infinity and goes till minus 1. This is a very interesting thing. This signal starts from minus infinity and goes till minus 1. Then alpha to the power z minus, the formula remains same. Then minus sign is part of the question we will have here. So we'll put k equal to minus n, so that now we have the expression going from 1 to infinity. So now what we'll do, which formula shall we go for? So what we'll do is, we'll use 0 to infinity, the formula for 0 to infinity. Then we shall subtract 1 from it, because z into alpha to the power 0 will be the first value of 0 to infinity, right? If that value we subtract from 0 to infinity, we will get this particular term only. Minus sign once again is part of the question. So minus of minus is a plus, then minus accompanied here. 0 to infinity of alpha is equal to 1 divided by 1 minus alpha. So you do the manipulation here and you end up getting the same Z transform, Z divided by Z minus alpha. Now what about the ROC? Now see here, ROC should be determined on those summations which usually go from any place to infinity. Either this is a nice spot to determine ROC, or maybe here. Okay, this term is also good, because we are bothered about magnitude. We are not bothered about the sign. Okay, we are bothered only about the magnitude. Okay. Now, be it 1 to infinity or 0 to infinity, be it positive or negative, if at all the number in the bracket here, if at all this number in the bracket here is greater than 1, then the entire thing is going to diverge, right? Then the entire thing is going to diverge. So my ROC, my condition is z into alpha to the power minus 1 should be less than 1, okay? Or magnitude z should be less than alpha. This is the condition. If at all my magnitude z is less than alpha, if magnitude z is less than alpha, then what's going to happen? See here, this is z, okay? Then this is alpha, okay? If at all my alpha, my z is smaller than greater than alpha, then what's going to happen? This entire term, okay, this entire term, okay, see this is z and this is alpha, right? So if this is greater than 1, then what's going to happen? This entire term is going to be less than 1. This is less than 1, this entire term is going to be greater than 1, okay? So that is why there is the condition. Now what was it that in the previous question, by the way? In the previous question, what we had, remember this particular term here, remember what we got here, the infinite summation. What we are getting here is z into alpha to the power minus 1 whole to the power k, okay? How did we get this? Actually it was alpha into z to the power minus 1 to the power n only, but then we substitute k equal to minus n, right? That is where this became z into alpha to the power minus 1, okay, after changing the limits. What about the previous question? What about the previous question? In the previous question, we had the infinite summation which had alpha into z to the power minus 1, okay? In the previous question, we had alpha into z to the power minus 1. Whereas in this particular question, since we changed the limits and the entire summation was on the other side, we are getting z into alpha to the power minus 1. That is why now the conditions are not alpha into z to the power minus 1 less than 1, but it is z into alpha to the power minus 1 less than 1. Hence we get magnitude z less than alpha as our region of convergence. So my ROC here is inside the circle. The first signal was a right-sided signal, infinite duration. So my ROC was outside the circle. The second question is a left-sided signal. That is why my ROC is inside the circle. What about poles and zero? Same, z equal to 0. So there is a 0 at origin. There is a 0 at origin and there is a pole at alpha. That doesn't change, right? That doesn't change. But then we saw two questions. Both of them had same signals, right? Both of them had same Z transform, even though the signals were different. So same Z transform, but they are separated in the ROC. Now got this particular thing. Okay, got this particular thing. Okay, so now what we'll do, yeah, let us see what next do I have. Yes. What about an impulse, by the way? What about an impulse? So impulse contains only a single signal, delta to the power delta of n minus k. Delta n minus k means if k equal to 4. If k equal to 4, the signal exists at 4, right? K equal to minus 3, okay, the signal, okay. This is only single signal, okay. Delta n minus k means here, okay. So what it is going to contain? X of n z to the power minus n. So amplitude is a single value, magnitude is 1. So it exists at k. So z to the power minus k. So this is z transform. So for what value of z may this x of z may go to infinity? If at all this z equal to 0, 1 by 0 is going to be infinity. Otherwise, it is always converging only for any other value. So my ROC is entire Z plane. Okay, my ROC is entire Z plane. So now, small time, let me revise what just happened today. Let me just revise. Okay, let me just revise. So what did we do, by the way? We started with this particular Z transform. We started with the Z transform. What is the formula? X of n, Z to the power minus n with the summation. Okay, we saw 5 problems today. 3 of the problems there had a finite duration. 3 problems had finite duration. Then remaining 2 problems had infinite duration. First thing we saw was for all these 3 finite duration signals, ROC was entire Z plane. ROC was entire Z plane. And what was ROC, by the way? ROC means those values of Z for which X of Z is finite. Now, this particular thing here. So this particular thing here, look what is the action of ROC. we always know, right? We always know one thing for sure, that if at all you happen to have, if at all you happen to have, okay, wait a second, and the glitch, okay. Now let me conclude this very quickly. Okay, it is like you can see alpha to the power n into u of n. If alpha was greater than 1, this was diverging. Alpha less than 1, this was converging. So what Z transform did was, it attached a Z to this alpha. It is like you having an oscillator with a feedback, right? Oscillator with a feedback, if at all the feedback is positive, it will go unstable, right? And it will go into oscillations. If the feedback is satisfying certain criteria, everything will be sustained. If the feedback is negative, then the signals will get damped or it can sustain. So this Z here that has been put along with alpha, that's what it does, right? It is like, a guy who is accompanying this alpha, so that it will decide, even if alpha is going to go bad, if at all you control this particular Z, you can still manage the stability. Okay, you can still manage the stability. So here we saw alpha would have gone positive, but then you have Z with it. So for Z greater than alpha, the stability is still maintained. Let me stop here. Let me continue tomorrow, and tomorrow we'll discuss, see a few more problems, and we'll conclude the properties of